enough to another water source that it wouldn't be the end of the world if they didn't have some water for one day of the year, or they could save it, then that might be an option. If not, then you increase the cost in order to ship. Yeah.
Does it hit the other contaminants out, or is it strictly these?
Yeah, that's a good question. So itself only gets out charged ions. But in both cases, whether you're doing reverse osmosis or electrodialysis, you would do a full series of pre-treatment to get out twigs and anything smaller, right? So get all big particles, and then you would almost always follow it up with UV disinfection, so UV light to do any of that. So no, you cannot use electrodialysis on its own, but you can also never really use our reverse osmosis on its own. Yeah.
Was your system constrained by maintenance requirements as far as bringing employees from remote village, as far as tools available?
Yeah, I actually could have showed that. So for the current RO, essentially I was trying to pick systems that required as much or less maintenance than the current RO plants, which have been shown to work. And so in those cases, there's an operator that's trained by Tata Projects. The operator goes to Hyderabad, does a week-long training. They learn what pressures are bad pressures to worry about. So they usually don't fully understand what's happening, but they know what to record. So they have a book, and each morning they're supposed to write down the pressure here, here, and here, write down the salinity here, here, and here, and if it's above a certain value, call another number, kind of thing. So a similar type system would work here. They also back flush the system, so that's kind of cleaning out the filters and stuff. So turning a nozzle. So as long as it's things that you can lineate into step 1, do this, step 2, do this, it's usually fine. And as long as there's, of course, some sort of backup company, NGO that's supporting the system in case something happens that needs to be fixed. Yeah. Yeah.
You said that you learned that the water aesthetic was an important thing after your interviews. Was that something that you got a lead on before, or someone told you that before? Was it something you had to determine entirely from the responses that people gave you?
So it is in literature. It's actually one of the funniest things, I feel because previous to going, I had looked at all of these inexpensive options for treating water and chlorination and all these other things because everyone is oh my gosh, diarrhea is killing people, we have to get out the bacteria, right? And so that's what I was focused on. Once I got there and kept hearing people use it's salty, it doesn't taste good, I don't want to use this, I don't want to buy it, it doesn't make it taste good. Once I kept hearing that over and over again, and then I looked into the literature on it, I found it. But I guess I didn't have a reason to look into that literature because at that point I was going into more food science and other psych journals, stuff like that, more so than the mechanical engineering side. And so I didn't necessarily go that route until I heard that from the users. But it's not that the data wasn't necessarily there. And to me, it's kind of ironic that it isn't normally considered as much as it should be. But yeah, so I can answer more at the end once he's done.
Yeah, I wanted to talk to the talk because I think this, I don't know, it looks kind of like an atom or something, or on The Simpsons, the nuclear power thing. But her mega Venn diagram is a really nice treasure map for how we had to figure this out by weighing both the socioeconomic and technical factors. And I think had we done one or the other, we may have missed something. All right, so now I'm going to talk about prosthetic knees, which is a similar type story, technical and socioeconomic. So what we're trying to do in my group is make a low-cost prosthetic knee that can enhance the mobility of people in developing countries. And the nickname is the AT knee, for all-terrain knee. This is just an artistic rendering of what it could be. Kind of cheesy. But so anyway, this is what we know about knees in developing countries. So in India alone, there's over 200,000 above-knee amputees. Worldwide, it's millions. And that the currently available prosthetic limbs cannot fully meet people's needs and can't replicate normal human gait. So to give you an example, this is what you most commonly see throughout India, which is a locked joint. And you can see this guy is having to kind of walk with, he's literally walking with a peg leg. And he has to lift his hip and swing his leg around. That's called circumduction. But it's pretty arduous and energy intensive. And other products on the market, this is an improved knee that came out of Stanford. It's better gait, but you can still tell, you could tell this guy's limping, right, if he had pants on. And so there's been work done on these low-cost prosthetic limbs. A lot of it was done like 40 years ago because these were the type of limbs in the US. But they require a lot more oxygen consumed per meter than healthy people, and they make people walk a lot slower. So these are the drawbacks. From a socioeconomic perspective, looking disabled may prevent you from getting a job because there's a lot of stigma against disability, or it may prevent you from getting married. You know, so the stakes in some ways are even higher in these markets because of the stigmas associated with disability. Now to contrast these limbs, here's an example of kind of the state of the art that you'd find in this country. This is called the Autobox sea leg, and it's a lot more efficient than passive legs, and it enables a person to walk a lot faster, close to as fast as a regular person. Issue is they're more than $50,000. Right? Way outside the price point of what we could do in the developing world. So when we started this project, it kind of started similar to the Jane project, where we've been working with Jaipur Foot for a long time, and they said we could really use a better knee on the market. And the core requirements we'd like you to meet is that you can replicate near normative gait, you can make it efficient to walk with, it can be stable on rough ground, so if a person stumbles, they don't just fall over because the knee collapses. And the price point in that market would be that the knee has to cost less than $100, right? And look at that comparison to $50,000, right? So big gap. So this again comes into one of these cost performance curves like I showed before. And we could contrast kind of the global scope of products of prosthetic knees and see where we lie. And again, we're in the situation where we'd love to be up near the sea leg, walking really normally, but we have to hit the price points down at lower levels. This is an updated version, by the way, of that Stanford knee, which has much better, I think, socioeconomic compliance. This one's a lot quieter, and you get this kind of natural kneecap shape on it. So it looks really nice underneath pant legs. So anyway, we have to create this disruptive solution again, and the idea is that we can meet the needs of these people, but if we do that and can provide the performance like up here, you know, we could again bring this product into global markets and hopefully disrupt these guys, right? And there's a $23 billion a year market for prosthetic limbs. So it's not small. So this is what we're trying to do, and we're trying to look globally from the start and see if we can make multi-market solutions. So anyway, what was interesting at the start of this is we had to identify like what the problem is and what would we need to solve, you know, to create a solution. And so you do the prior art search, and we know how healthy people walk really well. You can instrument a person in what's called a gait lab, you can put markers on their limbs, and you can measure how they walk and the forces they exert on the ground with this thing, which is a force plate. And so this is just showing your knee angle throughout your gait cycle. During stance, when your foot's against the ground, and during swing, when your foot comes up and swings forward. So we know how healthy people walk. We also know that with low-cost prosthetic limbs, they really throw off your gait. So this is showing with a prosthetic limb that you basically get no knee flexion during stance. And we also know the energetic disadvantages. And then we also know that with much higher end prostheses, they do a lot better. So they're energetically a lot better, they look more normal, and they provide a better benefit to the user. But the big gap in knowledge in this space that really mattered to us is nobody had ever figured out what would the ideal torque profile be that you'd have to develop in a prosthetic knee in order to achieve regular walking kinematics if your leg is much lower mass than a healthy leg. And why this is such a challenging problem is that a prosthetic limb on average is about 30% the mass of your healthy leg. So think about if you applied healthy body torque levels to a light leg, you know, your leg's going to go all over the place. So it really surprised us that this hadn't been figured out, but this was kind of the crux of the problem for us to create a solution. A passive, low-cost solution that would be appropriate for developing countries. So we started by looking at healthy data, healthy walking data, and you can model the one side of a human with their torso, upper leg, lower leg, and foot segments, and look at, you know, the ground reaction forces that a normal person makes, the masses of their limb segments, and how they move, because we know how healthy people walk. That's been recorded, right? And here's just a gait. This is your knee angle through the gait cycle of a healthy person. So we know those healthy kinematics. And then all we did was just do F equals ma to figure out how would the ground reaction force of an amputee differ from an able-bodied person, right? And your forces on your foot are going to decrease if you're an amputee because your limbs are lighter, right? And you can account for those changes in ground reaction force on the ground by knowing the mass difference between a healthy leg and a prosthetic leg, and by knowing healthy kinematics, right? You know the accelerations, and so you can back calculate how the forces should change on an amputee. And by knowing the forces at the ground and the kinematics, you can back calculate all the torques back up through the body and figure out what the ideal torque profile would be. So this was the validation of the model, looking at what we'd predict versus actual healthy person kinematics. And they were really close. The red line is showing, like, when we plug in normal values for people's legs, put in normal kinematics, how does the moment in each of the joints, the knee, the ankle, the hip, look compared to what's actually measured. So we showed our models pretty darn close. And then what that enabled us to do then is figure out how the torque profile changes in the knee and the power changes in the hip as we change the masses of all the limb segments. So this is going from healthy level, 100%, down to lighter and lighter limb segments. And we saw that you get actually pretty big changes, about 70% different torques in the knee during swing and about 40% different during stance, right? So quite big differences. So we were also able to codify how much energy could you save when you're walking by using a lighter leg. And intuitively, people have known this for a long time, because you just think about, if you have a lighter leg, you have less kinetic and energy in the system. You're not having to accelerate and decelerate that mass as much. So if you lower the segments of the mass of your leg segments down to about 20% of a normal leg, or 25%, you can lower the energy going into your hip by about 20%, which is quite a bit, right? So this was cool. This enabled us to codify how much energy would actually be reduced by lightening the limb segments. And why hip energy matters is because if you're an above-knee amputee, that's your only propulsor, right? That's the only place you're putting in energy to the system. The other thing it enabled us to do is that, and I want to touch again on our strategy here, is that we thought we might be able to replicate normal walking kinematics with only passive mechanical elements that would be cheap enough to use in a developing world knee that costs $100. So we did this study of seeing whether or not we could replicate this idealized torque profile, and that's in blue here. And this is for your, like, really common scenario with a prosthetic limb. It's a prosthetic foot, lower leg, and about 50% mass of your upper leg because you have some residual limb. So we knew that idealized torque profile, and we found that with a single linear spring and 2 friction dampers, we could replicate this ideal torque profile to an R-squared value of 0.9. So what was really exciting about this is this, showed like a roadmap towards a solution where it looks like we can create this high-performance knee that closely replicates normal kinematics, but with really, really low-cost elements. And the aim here is to make a knee that costs $100 that performs almost as well as these $50,000 knees. So from kind of the machine design perspective, what we were able to do is do the physics, work out the calculations, and see a strategy towards a solution, right? And we only saw that through the physics. But then there was the other side of this from the socioeconomic side that we had to figure out. And so we did a series of of interviews with 19 amputees. And the questions that we asked boiled down to basically 2 simple questions. And the reason we didn't ask people like on a Likert scale of like, rate this activity from 1 to 5, how difficult it is. People are like, 1 to 5, how does that correlate to what you mean by hard or difficult? Instead we asked yes or no questions, and this turned out to be really valuable because we just asked people, is each of 22 daily activities you might do, is it easy with your current prosthesis, yes or no? And if no, would it provide value in your life if if a new design was easier to do that activity with? So what came out of this, and we're still figuring out if the product of difficulty and importance is the best way to represent this, but we're trying to capture activities that are both really difficult and would add value to people's lives if they were not difficult anymore. But the top activities here are, the number one was sitting cross-legged, right? And what really stood out about that was we had never considered sitting cross-legged. That doesn't enhance your walking on flat ground. It doesn't enhance your kinematics. It's not something that, I think if you're just out in an interview setting, you would view somebody having difficulty with. Like, we knew squatting was a big issue because our partners told us that, and that makes sense because people defecate, or when they defecate, they have to squat, typically in India. But sitting cross-legged wasn't obvious. And I think what really, struck us here is, like, when we saw that, we were like, duh, yeah, people want to say Indian style in India. Makes a lot of sense. But I like this example because had we not figured that out, it could have hurt the performance of the product in the satisfaction of the user of the product, right? By being able to provide this functionality, we might be able to make a much better product, right? So we assess that, and so by putting together this technical and socioeconomic, we did all the physics, and this is a chart of showing your damping values that you'd want and your spring value, which are normalized by body mass, as a function of your foot mass, your lower leg mass, and your upper leg mass. So this gives us a whole design space of what components we'd want to use in our knee. And then we could add into that this full list of design requirements we got from talking to people, talking from that whole customer value chain that has to do with this product. So, here were the initial requirements by the partner. This is from follow-up conversations, things like walking on unstable ground, allowing squatting, meeting international standards. That's a big problem Jaipur Foot has. The lifetime this thing would need to have. And then again, these interview requirements that came out, particularly this one that we would have never guessed. So from doing all these activities, we got a really nice set of requirements, which I think has put us on a good trajectory for a solution. And I just wanted to give you an update where we are now. That work I just showed was finished a little over a year ago. Yash Narang, who did it, has since graduated. He's now a grad student at Harvard. But this is Murthy, who's working on the project now. So he's used all that analysis to start designing a physical knee. And here's a video of a guy walking with it just a month ago. And it's not perfect. It's got a bit of hyperextension, but it's not bad. It's getting there. And this doesn't have the full springiness incorporated yet, but it does have some damping in it. The reason I'm showing this picture right here is because what the knee is doing right there is called late stance flexion, where when you normally walk, when your foot starts leaving the ground, you actually bend your knee, right, as your foot starts coming off the ground. And it helps your foot to clear the ground. With all the other knees on the market right now, there's one actually that came out of Canada recently that can also do this. But with the conventional knees right now, you have to actually go all the way like to here before you can start bending your knee. Your foot has to leave off the ground. So you end up having a straight leg way longer than you want. And it throws off people's gait. So we're pretty happy with this performance, where it is. This was our first quick and dirty prototype. And it also locks during the early stance. So if you stumble with this, the joint stays locked. And then as your weight comes over your foot, it unlocks and lets you swing. So, it's going pretty well, and we would have never gotten here without all the analysis we did beforehand. And I put this picture in too because it's so important to iterate. Right, and so you can see Murthy's tuning up the knees, cranking down a screw to change the damping. But he did a nice design which enabled him to test different damping values. And this was the first of a bunch of knees we're going to make. We're going back in January with an upgraded design that has even more functionality. So we tried to test quickly, fail quickly if possible. And there was stuff that didn't work well on this, like the hyperextension. And then we'll go back to the drawing board. Yeah. Well, we capture that a lot here, right? Customization as far as spring and damping, but are you talking about socket?
Socket, length, and different injuries people have.
Yeah. So a lot of that is taken up by the socket design, which Jaipur Foot already does, and they custom make every socket, and they can do it in a day. It usually takes like weeks here, but it's super fast. I think eventually we probably don't want a socket that rotates around the residual limb. We'll probably put a joint at the knee that rotates. But you change length with pylon length, which is they already do with their other knees. So they're pretty equipped to do that customization. And off-the-shelf knees that you buy even in this country are not really modified as far as their physical structure between people. You change the lengths with the pylon, and with the socket. Yeah?
Have you looked at messing with the ankle? I think for all terrain, like the ankle joint might be more important than keep stability.
Yeah, we're also redesigning the foot. Yeah, it's a full system, and that's another good point, or that's a good point for another reason, that our analysis was predicated on the ankle walking normally, right? And then we were calculating what our knee would do, but we were assuming the ankle would walk normally. The challenge in that is your ankle is a net energy producer, right? It's a propulsor. So if you integrate the energy output versus the energy dissipated throughout the gait cycle with your ankle, more is actually being output. Whereas your knee is a net dissipator. It's actually a shock absorber if you integrate the energy throughout the whole gait cycle. So making a passive knee makes a lot of sense. You should be able to do it because more energy is dissipated. Making an ankle, you can't create energy. So we're already not perfect. But what we're doing on the foot project is trying to optimize how much energy we can store in return. And we're getting, one measure of how you look at that is the shape the foot makes as it bends against the ground versus the load applied to it. And so you can work out like how much energy is going in and out and how that shape changes. So if we look at our new prototype foot shape under ideal loading, like real human foot loading, the shape it makes is to an R² value of like 0.8 something, like 0.82 or 0.83. So it's pretty good, and we're storing as much elastic energy as we can to push off. So hopefully we're close. But it's a good point. And I think down the road with a foot too, we're probably going to have some like lateral compliance as well for walking on rough terrain. That's one nice thing about the Jaipur foot is it's rubber and it's flexible. Yeah?
So you showed the cost performance curve.
Yeah.
How much work do you spend understanding what the cost drivers are of the high performance products?
That's a good point. Some of it's markup, a lot of it's markup, right? So we do try to understand like how the prostheses are prescribed to people, but I don't know how much R&D is, how much cost is going into R&D cost is going into that overall cost. I don't know that specifically.
What about like materials or manufacturing costs?
We get a sense of it, yeah, because like the high-end knees are all microcontroller knees. They're basically like robots. So there's a lot of R&D money that goes into that, and they're also, fabricated. So they're, you have to make the circuit boards and the actuators and all that stuff, and they're often made of titanium and carbon fiber. So we do look at it from that perspective and may weigh like something like Delrin versus carbon fiber, or like spring steel versus carbon fiber, and look at how it behaves as far as storing and releasing energy. So we do look at it from that perspective. And I think, I won't go back to the cost performance slide, but I can very well see that in the future, if this works out really well, we'll have a developing world knee that costs $100 that's made out of like, cheap plastic and maybe steel. It'll be a little heavier, it might be a little clunkier, and then we'll make the super sleek US version that costs maybe $1,000 or $5,000, and that does have titanium and carbon fiber in it, but still uses the same basic technology, like a passive system with fewer elements. Yep.
How did you come up with the price point of $100? And are these knees sold at like a subsidy, or are they given away? Jaipur Foot, our partner, dictated that price point of $100. They said at that level, we think we don't think we'd have any barriers to distribution. We think we could distribute as many as we wanted. Their current knees, that locked knee joint, the hardware on it's only $10. And with the socket and everything, I think it's around 25 maybe. So it's a lot lower cost than what we're proposing.
But that price point came from the partner assessing what their capability to buy would be. And I think it's pretty accurate because a couple new knees that have come out on the market are right around there. That Stanford knee that I was talking about is about 80. And that the Canadian knee that I briefly mentioned is also right in the range of 100.
And the people who will be using this are in a position to pay that? Or
No.
give it away?
No, Jaipur Foot is a pure charity organization. They give away absolutely everything. Yep.
So can you sit cross-legged?
No, not yet. No, we haven't. This knee has all sorts of problems and doesn't meet lots of those requirements. And this testing right now is really on flat ground. You know, that's where we've mostly done it. We've done a couple stairs actually and ramps, but this is still early. Yeah? Yeah, Johnny?
Is material costs in manufacturing or mostly on knees are up at $60,000? Or is there another cost that goes into that?
I think it's primarily, well, I think it's R&D costs, right? Because they're paying their engineers. And I think it's just that the market will bear it. You know, they'll bear the huge markup. I don't think the manufacturing cost is anywhere close to that. You know, it's probably a fourth, I would guess, or, you know, between a fourth and a half. Yeah, so there's the middleman, like the prescribers taking a cut of the cost, et cetera.
It just seems like an awful lot for
Yeah.
medical device.
I agree. And a cool side note on this project is the VA has been excited about what we're doing. We're going to submit something this year to them. But we're the cheapest game in town. You know, we're trying to cut the cost by 1,000 times. And they appreciate that because right now a veteran might have 5 different legs that they use, each one costing 50 grand. And it's a huge expense to the VA. So having just one leg that costs like $1,000 would be really valuable to them. I also think this is a cool project because, from a research perspective, because we had to like back way up from what existing state-of-the-art is in prostheses, right? State-of-the-art is robotic, high performance. But we had to back way up from that and say, okay, how well could we do with passive? And then that takes us down another track. So that's pretty cool. It's an example of how I think these problems in emerging markets can really drive new science. Yeah,
So I
John.
really like the fact that the prototype right there is very adjustable. Have you let somebody have it for a month and see what they adjusted to, and what might you learn from that?
No, we haven't. We haven't been anywhere close there. This was a couple-week field trial where we only tested 3 or 5 people, and it was really like supervised. Yeah, this was still very early on, and this is really a bench-level prototype. This is not anywhere close to, I think, something that would stand up in the field for weeks. Yeah.
So the Stanford knee?
Yeah.
Is it also targeting sort of developing world applications?
Exactly. Yep.
Are they like, what's the relationship like with them? Is it competitors?
No, it's really good because, I like that you're asking that. So I had to give this slide in front of them a couple during the summer, and here's their knee, and we're trying to be way out here, right? And yeah, and so, no, I didn't pull that card. No. I think rightly so, Stanford has made a huge leap going from here to here, right? And they deserve credit for that. But this is based, and they'll admit this is based on about a 50-year-old technology that was around in the States way back when. This polycentric knee, it uses a 4-bar mechanism, has been around a long time. They just made it sleeker and they made it cheaper, right? That doesn't mean there's not room to jump performance even more, right? And they appreciate that we're trying to do that. And we're taking on, I think, a high risk because we don't know if it's going to work. And it's a huge expense in time, right? So I think it's now a company called D-Rev that makes this. It's left Stanford and it's actually commercialized. They feel like benefiting the lives of people with disabilities in developing countries is great, whoever's doing it, and really pushing the technology is also great. So I'm not trying to imply at all that this is a bad product. It's not. But there's room for improved performance, and that's indicated by improved performance way up here, right? But it's getting that type of performance down here that's really tricky. Cool, yeah?
Have you worked with any of the companies that make the high-end knees? Or
No.
try to get their data? I feel like to redo all the data that they have on like gaits and
It's proprietary. They don't publish it. I mean, we've certainly looked. My uncle's a prosthetist too, so we talked to him. We also have taken apart a bunch of knees to try to reverse engineer it. But no, we can't really tell like how optimized the current knees actually are. Like what was the science behind them? You know, if it's more of an iterative approach where they got better and better and better, or if they've actually, maybe they've already worked out all that we've done, but it's not public. Yep. Cool. All right, so we've got a few minutes now if we want to talk about your projects. We've got about 10 minutes. I had one last slide to show that we've got an awesome guest speaker coming on Wednesday, Shashi from Lawrence Berkeley National Labs. But he's leading LIGHT, this center that's very much like the Tata Center here, actually. They're trying to come up with really disruptive solutions for emerging markets, but also commercialize them, which is pretty cool. I'll post out of poverty readings tonight, and just keep going with your teams and remind you that your strategy presentations are going to be October 8th. So open up questions about your projects. How's it going? Yeah.
So we could share a little bit. We have met a couple times, and we actually talked to our sponsor on Friday.
Yeah.
So that was cool. They seem to be very consumer-facing or customer-facing, so they have spent a lot of time getting data on 400 people that they surveyed to really understand what the user wants. And
which company?
OSHA.
OSHA, yeah.
So, which is really cool. I think a big challenge for us is going to be scope and just like getting to a point where we can figure out what we're sort of trying to engineer. So it's really cool to see them on the like user-facing side and then understanding, getting things like quality of life, and if this product's more expensive, it's seen as cooler, so we want to buy it, or we want to customize the design of it to fit in our house and how it looks. So that's kind of cool to see from a design side, and I think it'll be hard for us to get back and scope to the engineering side, but that's a cool challenge.
Yeah, Susan and I were talking about this the other day. Like, I think there's a lot of physics you can add with that too. Like how fast does the air have to move? How does the temperature of the air you're blowing change how you feel? All that stuff. Yeah.
So like we went out and did a bunch of research, playing with fishing reels and stuff. And if we were to go back and try and make something like you have with the quality cost curve, what's sort of your approach of doing that? Do you kind of plot them and then go through the curve, or do you try and place products along the curve?
Yeah, when we do this, we try to, we first try to understand the performance and price needed in emerging markets. And then if that performance is similar to the high end of rich markets, we know that we could probably make a version in rich markets that costs less but performs well. Though there's intentionally not units on those graphs, right? They're more qualitative. On price we can usually put, units. But yeah, performance, it's hard to judge sometimes. So I don't know if that answers your question, Andrew.
Yeah, it kind of does,
Yeah, I think, so in your case specifically, I think Okuma has a good sense for what price point would work for that reel. They have a sense of what other competitors offer globally in the market, right? And I think if you ask them and said like, okay, say we can offer this same reel that you have for half the cost in the US, how would that affect your business, right? That's kind of my approach I would take, because I think they probably have a really good sense of that. And they may say, well, even if we could make it cheaper, we wouldn't sell it for any cheaper, because there may be a perception, to the user that it's lower quality or something. They may want to keep their current design, which has more bearings, which may not even be as robust, because it fits nicely in the market somewhere. But I try to get that perspective from them. Yeah.
Yeah, so we talked to Elliot Prasad last night.
Yeah.
One of the things that surprised me was they gave us a price point of $150 out of pocket.
Yeah.
And they said that would be accessible not only to middle class, but to low income. And I'm kind of struggling to see how like a low income Indian family, like $150 is kind of expensive,
Make them define
even
low
US
income.
terms.
Make them define
Yeah.
what they're saying is low income. Because that's hugely different if it's, if they're making less than $1 a day versus if they're saying, often it's assumed that if they make less than $1 a day that they're kind of not in that category at all. So there's kind of like, there's always going to be a category that just has no money, right? That is never going to be able to afford anything that you make no matter what the cost is. And that's not the category that most of these projects are targeted at. So you have to have them like what is the monthly salary or whatever, or like the type of person that they think can afford it. Because you're right, the bottom, the mom and the bottom cannot afford that.
Yeah. I'd also ask them if that price is within their kind of cost distribution structure, their kind of Robin Hood structure, because you know how they work, right? They charge more to more wealthy patients, and the procedure that those patients get versus poor patients is like exactly the same, but what those wealthier patients pay for is like a better waiting room, better hospital bed, when they stay after, and so they're able to subsidize the costs of poorer patients. So I would ask them if like the actual price that a poor patient would pay would be $150, or if that's just the price of the product. Yeah, because it may be affordable within their structure. Yeah.
Yeah, so Tom and Nano team had a chance to meet with the two engineers from
Yep.
Neil and Smita, and what was really interesting, a lot of different takeaways, but one of them was that it's as much of a perception challenge as an engineering challenge. So trying to figure out where we allocate our resources as far as changing perception of the sound quality and also actually fixing sound quality. And that goes back to saying maybe the sound quality itself needs to change from sounding more like a lawnmower to something a bit more high-end. And it's hard to, it's very subjective as to what exactly it sounds like, where people get that view from.
Yeah.
So they're kind of stuck with that too. They've been working on it for over 6 years. It's a particular problem.
Mm-hmm.
And trying to get a fresh advice.
Yeah, they want out-of-the-box ideas. Well, I think a strategy you could take with this is take a product that sounds good and see if anybody has quantified what about it sounds good. If it's a frequency or loudness or what. Like we were talking about the Olfia 500s or something. I don't know if anybody has quantified what that sound actually sounds like.
They're going to try to provide some resources to us to say